What's up everyone and welcome. In this episode, we're going to talk about a weakness in Microsoft's WPBT capability that can allow an attacker to run malicious code with kernel privileges. This is a long one and some of the information is pretty complex, but it is important for all Windows users.
Oh, drat these computers. They're so naughty and so complex. I could pinch them.
The Eclypsium research team has identified a weakness in Microsoft's WPBT capability that can allow an attacker to run malicious code with kernel privileges when a device boots up. WPBT is a feature that allows OEMs to modify the host operating system during boot to include vendor-specific drivers, applications, and content. Compromising this process can enable an attacker to install a rootkit, compromising the integrity of the entire device. The issue stems from the fact that while Microsoft requires a WPBT binary to be signed, it'll accept an expired or revoked certificate. This means an attacker can sign a malicious binary with any readily available expired certificate. This issue affects all Windows-based devices going back to Windows 8 when WPBT was first introduced. Eclypsium has successfully demonstrated the attack on modern, secured core PCs that are running the latest boot protections.
Then all you do is click the shutter and presto. Golly, that sounds simple enough.
This weakness can be potentially exploited via multiple vectors, like physical access, remotely, and supply chain, and by multiple techniques, like malicious bootloaders or DMA, etc. Organizations will need to consider these vectors and employ a layered approach to security to ensure that all available fixes are applied and identify any potential compromises to devices. Microsoft recommends customers use Windows Defender application to limit what is allowed to run on their devices. WDAC policy is also enforced for binaries included in WPBT and should mitigate this issue. We recommend customers implement a WDAC policy that is as restrictive as practical for their environment. You can find documentation on WDAC. Now, Advanced Configuration and Power Interface, or ACPI, is a specification that provides hardware abstraction layer between a system's firmware, its operating system, and the components of the device. ACPI was originally developed in order to let operating systems configure and manage power of hardware components within the system instead of relying on like BIOS and UEFI firmware. By moving this control to the operating system, ACPI opened the door to more dynamic and complex power management decisions that could be coded into firmware, or then could be coded into firmware. So you move the control of, let's say, hardware power usage to the operating system as opposed to how it used to be controlled in the firmware, which gives you more flexibility. Now, at a functional level, ACPI works by using ACPI tables. These tables are loaded into memory by the firmware during the boot process, and it tells the operating system what components are on the system and how they can be managed. Windows Platform Binary Table, or WPBT, is an ACPI tablet first introduced in Windows 8. And while ACPI was originally intended to give the operating system more control, WPBT can give firmware a foothold in the operating system. So, ACPI was trying to give the operating system control, let's say, into the firmware or the components into power management. Now, WPBT gives the firmware a foothold or access to the operating system. Now, Microsoft describes the WPBT as follows. The WPBT is a fixed advanced configuration and power interface table that enables boot firmware to provide Windows with a platform binary that the operating system can execute. So, WPBT allows the firmware to pass a binary to the operating system and say, hey, execute this, because I want to install, I want to make sure that the drivers for this particular Wi-Fi card or RJ45 or whatever the component is, it wants to give it more control. So you pass a binaries that the operating system can then do power management or any other type of configuration to that component. Now, the binary handoff medium is physical memory, allowing the boot firmware to provide the platform binary without modifying the Windows image on the disk. This functionality was intended to let OEMs include important files, drivers, like I just mentioned, or executables for the system without needing to modify the Windows image on disk. The technology has been used by a number of vendors, including Lenovo, Asus, and many others. By executing files and modifying the operating system, This type of functionality can be seen as a vendor-specific rootkit.
Too bad. Do you have dizzy spells? Do you see spots before your eyes? Do your ears ring? Are you subject to fits? So am I. Maybe that's what's the matter with me.
Acclaimed researcher and co-author of Windows Internals, Alex Ionescu, has been calling out the dangers of WPBT as a rootkit as early as 2012, and he continues to do so today. In June this year, Eclypsium publicly disclosed BIOS Disconnect, a set of 4 vulnerabilities that allowed them to gain remote execution within the firmware of a device during a BIOS update. Notably, they were able to perform this attack on the most recent and secured Dell platforms, including secured core PCs. Eclypsium subsequently presented the full technical details of these vulnerabilities at DEF CON 29, during which they showed a demo of an exploit on a secured core PC laptop with all available protections switched on, ending with a malicious executable being deposited in the Windows startup folder. While their talk detailed how they compromised the BIOS update process, they did not show exactly how they were able to place that executable in Windows startup folder. For that piece, they turned to WPBT and discovered an interesting weakness along the way. By compromising the firmware update process, they were able to load their own implant DXE driver, which controls various boot-related functions. Since UEFI ACPI protocols allow drivers to modify ACPI tables, they were able to add a new WPBT table of their choosing. The WPBT table specifies the actual location of the system binary that Windows will execute. So, WPBT has an address, and that address is to a binary, let's say from the OEM, either it's from the ASUS motherboard company or from Hewlett-Packard or Lenovo, right? And that application is supposed to make changes to your operating system to allow you to do better power management, as an example. Well, they were able to change that address that it points to a malicious binary. So, as a result, they were able to use their malicious driver to create a WPBT table pointing to the payload of their choosing. Alternatively, they could have patched an existing table using techniques such as shown in the signed UEFI shell project on GitHub. However, this officially should not have worked, as WPBT requires any binaries to be properly signed. Now, Microsoft's WPBT code signing policy states, all binaries published to Windows using the WPBT mechanism outlined in this paper must be embedded, signed, and timestamped. These images should be linked with the integrity check option and signed using the sign tool command line tool with the /nph switch to suppress page hashes. However, testing revealed that this check will pass even if the code signing certificate has been explicitly revoked. To highlight this, they signed their malicious code using a hacking team code signing certificate that was revoked in 2015. This and many other expired or revoked certificates are readily available to anyone on GitHub. This particular cert was revoked when the company's tools, including a UEFI rootkit, were exposed in a major breach. They used the certificate just to highlight a particularly egregious example, but the same process would work with other revoked certificates as well. This attack is also significant because it allows an attacker to drop a malicious file in the operating system even while BitLocker encrypts the disk. BitLocker would prevent other types of threats such as the hacking team implant, which used firmware to directly write the malicious code to disk. However, in the case of WPBT, an attacker could avoid BitLocker since the malicious file is pushed to the operating system and stored in the C Windows System 32 and then run on startup.
I think you've got something there, buddy.
It is important to note that this weakness can be exploited in a variety of ways. In their example, Eclypsium started in a particularly privileged position, having already compromised the system's firmware during the update process. However, this type of attack is possible using any technique that can write to memory where the ACPI tables, including WPBT, are located. This can also be done by a malicious bootloader that could be introduced by the widespread boot hole vulnerability or via a DMA attack launched from a vulnerable component or peripheral. With this in mind, security teams should consider the following potential threat vectors. Attack with physical access. An attacker with physical access can launch a DMA attack to directly read and write system memory and thus patch a WPBT table. Some DMA attacks can be performed without opening the device chassis, while others will require the more invasive step of opening the device itself. Countermeasures. Security teams should scan devices to identify components that are vulnerable to DMA attacks and verify that all vendor DMA protections are properly enabled. Another vector, remote attacker. Remote attackers can compromise devices in a variety of ways. Malware such as TrickBot can identify vulnerable UEFI firmware that can be compromised directly. With control of firmware, the attacker could directly control WPBT. Likewise, malware or remote attackers could use vulnerabilities such as boothole to run a malicious bootloader capable of updating WPBT. Countermeasures. Security teams will need to scan devices for any of the many vulnerabilities that could allow attackers to compromise the firmware or boot process. Teams will likewise need to verify that all available vendor protections are enabled, including protections included with UEFI, chipset vendor, OS vendor, and any OEM-specific protections. Teams will likewise need to make sure their UEFI DBX revocation database is up to date. Teams should verify the integrity of all firmware, scan for known implants, and monitor the behavior of firmware on the device. The next is a supply chain attack. Malicious firmware can also be introduced in the supply chain or the vendor update process. In their example, they were able to compromise the valid firmware update process of the device. So it's important to note that such a compromise can happen before as well as after a device is acquired. In addition to compromises to UEFI BIOS firmware within DMA-capable devices such as SSDs, network adapters, or PCI interfaces could lead to a corruption of the WPBT table. Countermeasures. Security teams will need to verify the integrity of all system and component firmware to verify that it matches the approved vendor-supplied version of firmware. Again, teams will need to scan for the presence of known firmware threats and implants. Additionally, it is particularly important for teams to monitor firmware for any abnormal or anomalous behaviors, since in the case of a supply chain attack, the approved vendor-supplied firmware may already be compromised. Since this is a weakness in Microsoft's implementation of WPBT, the issue will affect virtually all Windows machines going back to Windows 8 when WPBT was introduced back in October 2012. Microsoft recommends customers use Windows Defender application control to limit blah blah blah. We've already read this. We've already heard this. In Eclypsium's research, they have not found documentation from Microsoft detailing how to disable WPBT. However, others have published options such as Drop WPBT project on GitHub that organizations consider. Now, as with any unofficial solution, organizations should evaluate these options and apply them at their own discretion. So, what did we learn? First, check your machine. This affects, again, virtually all Windows machines going back to Windows 8. It is important, yes, to patch, including firmware, but this issue further highlights the complexity and challenges involved in securing the boot process of modern devices. In recent years, chipset vendors, operating system vendors, and OEMs have rightly developed a variety of features and capabilities to help make the boot process more secure. This includes things like UEFI Secure Boot, Intel's Boot Guard, and Microsoft's System Guard, System Management Mode, or SIM, protections, and BitLocker. Microsoft's Secured Core initiative is an umbrella term that includes a collection of these protections that can be implemented by OEMs to build Secure Core branded devices. Now, Secured Core covers a variety of areas ranging from establishing the root of trust on devices and kernel protections to visualization-based security. However, it's important to remember that in reality, we're talking about many technologies and many different vendors working together. Details will vary from OEM to OEM, which opens many opportunities for mistakes or vulnerabilities. A weakness in the chain can undercut the integrity of the entire process, allowing issues such as a weakness in WPBT, insecure firmware process, or other issues to provide adversaries with a path around these protections. So, it was a lot, it was a mouthful, it was long, but again, very important for all Windows users. And with that, I say thanks for watching. Don't forget to share and subscribe if you haven't already, and smash the bell if you haven't already, and I'll see you on the next episode. Take care.